Hello, students! This is an educational video created by Scholars Academy for CBSE Class 9 students. We're going to be talking all about motion today, and trust me, it's going to be a lot of fun. Okay, let's take a quick look at our agenda for today. We're going to cover 1. Distance and displacement, 2. Speed versus velocity, 3. Acceleration and changing pace, 4. Graphing object motion, 5. The equations of motion, and finally, 6. Uniform circular motion. Let's get right into it.
Section 1. Distance and displacement. We'll kick things off with some concepts you probably already experience every single day, like just walking to school or taking the bus.
So, here's the deal. While distance tracks every single step you take on your journey, displacement only cares about two things: where you started and where you finished. Imagine walking all the way around your entire school block and ending up exactly where you started. Your distance? That might be a whole kilometer. But your displacement? Zero. Absolutely zero, because you haven't actually moved away from your starting point.
Section 2. Speed versus velocity. Let's see how throwing direction into the mix completely changes how we measure our pace. Now, what's really interesting here is the huge difference between just moving fast and moving with a specific intent and direction. Speed is simply how fast you're covering ground. But velocity? Velocity is basically speed with a compass. It's not just driving 50 kilometers an hour. It's driving 50 kilometers an hour straight north.
Let's tackle our first numerical problem together, step by step. Our problem states that an object travels 16 meters in 4 seconds, and then another 16 meters in 2 seconds. First up are given values. The distances are 16 meters and 16 meters, and the times are 4 seconds and 2 seconds. Next, what's our formula? Average speed equals total distance divided by total time. Now for the calculation. 16 plus 16 gives us 32 meters for our total distance. 4 plus 2 is 6 seconds for our total time. Finally, 32 divided by 6 gives us our final answer of 5.33 meters per second. Moving on to an odometer problem. If a car's odometer goes from 2,000 to 2,400 kilometers, our given distance, s, is 400 kilometers. The given time, t, is 8 hours. Our formula here is average speed, v, equals distance, s, divided by time, t. So, calculating 400 divided by 8 gives us 50 kilometers per hour. But wait, physics relies on standard units. To convert this into meters per second, we multiply our 50 by 1,000 meters and then divide by 3,600 seconds. This leaves us with a final answer of exactly 13.9 meters per second.
This swimming example with Usha is brilliant because it really shows what happens when you return to your starting point. Usha swims 90 meters one way and 90 meters back in exactly 1 minute. Let's list out what we're given. The total distance is 180 meters, the displacement is 0, and the time is 60 seconds. Now for our formulas. Average speed is distance over time, while average velocity is displacement over time. Let's run the numbers. Speed is 180 divided by 60. Velocity is 0 divided by 60. So our final answers are an average speed of 3 meters per second, but an average velocity of exactly 0 meters per second.
Section 3, Acceleration and Changing Pace. Now, we're introducing the real catalyst of change. What happens when we hit the gas pedal or slam on the brakes?
Acceleration simply tells us how quickly our velocity is changing. Are we speeding up? Are we slowing down? The formula for this is a equals v, which is final velocity, minus u, which is initial velocity, all divided by t for time. And remember, the standard SI unit here is meters per second squared. Let's look at Rahul on his bicycle. In case 1, he speeds up from rest. So our given initial velocity, u, is 0. His final velocity, v, is 6, and time t is 30 seconds. Using our formula, a equals 6 minus 0 divided by 30, that gives us a final acceleration of 0.2 meters per second squared. But check out what happens in the second case. He applies the brakes. Now our given u is 6, our v is 4, and our t is 5. So 4 minus 6 gives a negative 2 divided by 5, which equals a final answer of negative 0.4 meters per second squared. His acceleration is actually negative because it's acting directly against his direction of motion.
Section 4, Graphing Object Motion. Let's take all these numbers and turn them into pictures by seeing how motion behaves on a graph.
A perfectly straight line on a distance-time graph visually proves a core concept. When an object travels equal distances in equal intervals of time, it's moving with uniform speed. If time is on the x-axis and distance is on the y-axis, a straight diagonal line means the pace literally never changes. It's totally predictable and steady.
Section 5, the equations of motion. All right, time to dive into the absolute math engine of this chapter.
You absolutely need to memorize these 3 formulas. They are your master keys for solving basically any uniform acceleration problem in physics. The first one, v equals u plus at, relates velocity and time. The second, s equals ut plus 1/2 at squared, helps you find distance or position over time. And the third, 2as equals v squared minus u squared, connects position and velocity without even needing to know the exact time interval. Let's see them in action. By methodically listing our given values and converting our units first, we can totally avoid those common algebra mistakes. A train starts from rest, so our given u is 0. Final velocity, v, is 72 kilometers per hour, which we immediately convert to 20 meters per second. Time, t, is 5 minutes, which is 300 seconds. First, to find acceleration, we use the formula a equals v minus u over t. So 20 divided by 300 gives an acceleration of 1/15 meters per second squared. Next, using our third equation of motion, 2as equals v squared minus u squared, we can find the distance s. Calculating 20 squared divided by 2 times 1/15 gives us our final answer, exactly 3,000 meters or 3 kilometers. The crucial trick here is using the first equation to find our acceleration and then seamlessly substituting that into the second equation to find our distance. A car accelerates from 18 to 36 kilometers per hour. Here's what we're given. U is 5 meters per second, v is 10 meters per second, and t is 5 seconds. Using our first formula, acceleration is 10 minus 5 divided by 5, which equals 1 meter per second squared. Okay, now let's plug that right into our second formula. S equals ut plus half at squared. We get 5 times 5 plus half of 1 times 25. That gives us 25 plus 12.5, resulting in a final answer of 37.5 meters covered. This next example brilliantly illustrates why maintaining a safe distance between vehicles on the road is absolutely critical. Even when slamming on the brakes, a car still travels 12 meters before fully stopping. Let's break down the math. The brakes are applied. We are given an acceleration a of -6 meters per second squared. The time t is 2 seconds, and final velocity v is 0. First, we find initial velocity u using the formula v equals u plus at. 0 equals u plus -12, so u is 12 meters per second. Next, we find distance s using our second formula. 12 times 2 plus half of -6 times 4. That is 24 minus 12. The final answer is 12 meters. See? Physics literally proves why tailgating is a terrible idea. Section 6. Uniform circular motion. Finally, let's explore what happens when an object's direction is constantly changing, even if its speed is perfectly steady. Here's a real mind-bender. Even though an object's speed might be constant, the continuous change in direction means the object is technically always accelerating. Remember earlier when we established that velocity includes direction? Well, when you move in a circle, your direction shifts at every single millimeter. Because your direction is changing, your velocity is changing, which means you are accelerating, even if your speedometer stays exactly the same. We calculate this velocity as 2 times pi times the radius divided by time. I want you to think about this surprising fact of circular motion as you continue exploring physics. Imagine an athlete in a sports meet spinning around and finally letting go of a heavy hammer. Which exact direction will it actually fly? Does it continue to curve through the air, or does it do something completely unexpected? It actually flies off in a perfectly straight line, matching the exact direction it was moving at the very split second of release. But why? Why does it just refuse to keep curving? Well, that requires a deep understanding of inertia, which we will explore next time. Keep observing the world around you, because physics is quite literally everywhere. Keep studying hard, and we'll see you in the next educational video.